In today's episode, John is joined by Dr. Michael Tremmel. Dr. Tremmel is a YCAA Fellow at Yale University and received his PhD from the University of Washington and his bachelor's degree from Northwestern University. He uses hydrodynamic simulations of galaxy formations to understand how galaxies and their supermassive black holes evolve over time. He's particularly interested in how supermassive black holes behave during galaxy mergers, with an emphasis on making predictions relevant for future gravitational wave observations with LISA and pulsar timing arrays.
Welcome everyone to Event Horizon with me, John Michael Godier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Dr. Tremmel, welcome to the program.
Thanks for having me.
Now, Doctor, you work with supermassive black holes, particularly the merger of such things when two galaxies merge, which is in the future for the Milky Way and the Andromeda Galaxy. So could you give us some kind of an idea? What happens first when two galaxies merge and these black holes are moving towards each other? What is the process in which they merge?
That's a good question. So yeah, this is exactly what my recent research has been all about. It's actually pretty complicated. When two galaxies merge, right? Remember, a galaxy is a collection of a lot of gas and a lot of stars, also dark matter. So all of that stuff is interacting with one another to bring the galaxies closer together, right? So you can imagine Andromeda and Milky Way, for example, they're coming closer to each other. They're gravitationally bound, and then when they start interacting, right, there's all this complicated exchange of energy and angular momentum between all their stars and gas and all of that. And eventually, the main component of those two galaxies loses enough of that energy, that initial orbital energy that they have, and come together and merge into one single galaxy. So in the case of Andromeda and the Milky Way, there's actually a few different YouTube videos and stuff that you can watch where people have tried to simulate roughly what such a merger would look like, even from inside the Milky Way, which is pretty cool. And lots of stuff happens to the galaxies themselves throughout this process. They often change the way they look. They often will go through a starburst where all that gas that exists sort of gets compressed all at once and forms a lot of stars. So even without the black holes, the merger of two galaxies, massive ones, especially like the Milky Way and Andromeda, they can be a really interesting process in their own right. And then you have the black holes. So the black holes, in these cases at least, exist in the centers of the galaxies, and they're sort of the densest part of the galaxies. And so as the galaxies are merging, the two cores of those galaxies, you can imagine like the dense stellar structure, the center of these galaxies, will eventually come together and merge themselves, and then the black holes will become close enough to become mutually bound themselves, right? So the important thing to realize is when things are far away, when these galaxies are far away, the thing that's most important is the two galaxies interacting, their mass, their structure interacting with each other. Only when the black holes get pretty close, say on the order of a few light years, let's say, do they actually become mutually bound to one another and create a binary black hole. Right, so before that, you can't really call two black holes binary black holes. They're two black holes in the center of two separate galaxies. But then once they come close, then they become their own system. And that's where gravitational wave interactions become more important. That's where things like LISA, the new gravitational wave detector that's being launched in the early 2030s, will really shine, right? That's the sort of system that those things will detect, these binary black holes interacting with each other gravitationally. So the last step in the process to merging. As they emit those gravitational waves, that's sort of their last moments before they fall together to become one more massive, supermassive black hole.
Are there any wild cards? In other words, can the dynamics be such that a supermassive black hole might get ejected in this process?
Oh, yes, definitely. So there's the more conventional idea where you have something called a gravitational recoil. So yeah, black holes are complicated, right? So they're technically singularities, so they have no size themselves. We consider the size of a black hole to be their event horizon, where light can't escape anymore. But technically speaking, right, a black hole is a black hole because it's a singularity. All that mass is crammed into an infinitely small point. Nonetheless, black holes themselves have angular momentum. They have spin, sort of like subatomic particles also have spin, like a proton and electron have spin. They have, even though they're so tiny, they don't really have much of a size to them. They're still spinning in some technical sense. And so the black holes, when they merge, will have some angular momentum themselves. You can think of this as they've accreted gas throughout their whole lives to grow to be so massive. All that gas that they've eaten has had some rotation to it, and they've consumed that rotation and made it their own. So these two black holes, inside of them, they have this rotational velocity, this spin value that's come from all of these billions of years of growing from gas. And it ends up, if you do the calculations, when two black holes merge, if their relative spins are misaligned with one another, then the gravitational waves that get emitted when they merge will not be isotropic. They won't be evenly distributed around the black holes. They won't be emitted in a spherical way. Rather, one direction will have more gravitational waves than another one. And so gravitational waves carry with them momentum, just like anything else, just like light even carries with it momentum. And so when those gravitational waves get emitted, if they're not emitted equally in all directions, they'll actually transfer momentum to the black hole, right? So you have a black hole merger happen, and rather than it sort of radiating away gravitational waves in all directions, there'll be one preferred direction, and then it'll get pushed in the opposite direction. Just like if you're sitting in space and you toss a hammer in one direction, you fly the other way to conserve momentum. The same thing would happen to those black holes. And so when they merge, they can actually get pretty strong kicks. Could be hundreds of kilometers per second, but the theory on it is still, we're not sure what we would expect to see in terms of the magnitudes of black hole spins or how much they should be misaligned on average. And a lot of that depends on what you assume, as I said, how that complicated interaction that leads to a binary black hole in the first place, how that happens can also affect the final alignment of those spins. But if they are misaligned, then the black hole can be kicked away. And if it's powerful enough, it could be kicked pretty far away from the center of the galaxy. And a lot of people are doing some simulations to try to understand whether or not this, how much this could actually remove black holes from galaxies altogether.
The dynamics of that must be crazy. So if you get a black hole that's kicked out during a galactic merger, what happens to things like its accretion disk? Does that get all torn off and it just becomes a naked black hole? Or what would happen to the black hole as it got ejected?
That's also a really good question. So I think there's been lots of work, again, very uncertain stuff, right? There's lots of assumptions that go into this because we've never seen such a thing before. And there's also lots of uncertainty in terms of the physics of accretion disks in the first place. But I think what's most likely to happen is that the black hole gets ejected away, but it's still, around the black hole is still dominated by the black hole's gravity. So most of the stuff very nearby, most of the gas in the accretion disk, and probably even some stars around the black hole, if there's a lot of dense stellar cluster around it, which there often are, that stuff will probably follow the black hole as it gets ejected away. It's not so dissimilar from stars, actually. So binary stars, they can also get kicked from supernova explosions that also sort of radiate energy away in a non-spherical sense. And when that happens, if the star is in a binary, it can affect the binary orbit, but it can also pull the other star along with it. And the same thing probably would happen to the accretion disk. It'll probably fly along with the black hole. The problem is that accretion disk is going to no longer have the gas supply of the galaxy to feed it. And so probably the period in which the black hole is still actually accreting matter is probably short-lived after that point. So it flies away, brings some gas along with it, but pretty quickly it's gonna eat all that gas up and be left with nothing because it's left the center of the galaxy where all the gas is in the first place. But that's sort of the challenge, is to understand whether or not we can actually detect these black holes. If black holes have been ejected in the past, would they be able to be detected from their accretion. If there's still some accretion happening, how long does that last? Would we expect to see black holes very far away from the centers of galaxies that are very luminous, that we really haven't seen before? Very uncertain at this point.
When a black hole, say it loses its accretion disk or eats it, so to speak, and it can no longer replenish it, the only thing it's going to be emitting is Hawking radiation, right? So it should essentially be virtually undetectable?
More or less. So there are, the only way to detect it at that point then would be gravitationally. If there was some way to detect its gravitational influence. That's actually a lot of the ways we detect black holes now, is through the gravitational influence it has on nearby stars or gas. So if there are any stars nearby still, so maybe if the black hole is able to take with it some stars, that's one possible way, but that sounds like a very difficult observation to make even then. So yeah, short answer is it's probably going to be really, really hard.
Would seem to me that you would have to watch that for a very long time. If it's dragging stars with it, you're probably looking at centuries, if not thousands of years of observations, right?
Yeah, generally what you would hope to do is if there's a whole population of these black holes that exist out there that you're able to see. It's actually not, it's not so much that you need to view this whole evolution as it happens, right? The idea would be you're predicting, okay, if this is going on, then I'd expect to see in some cases that there's a black hole, many, many thousands of light years away from the center of a galaxy, and I expect there to be some stars still around it. Could you detect those stars and their motions just by looking at their velocities? We can do that now. You don't need to actually see the stars rotating around the black hole. For example, you can just detect their sort of instantaneous motions by looking at how fast they're moving currently. And that could, in theory, tell you there's a black hole there, just like we do at the centers of galaxies a lot of the time, is look at their instantaneous velocity of stars and infer that there's some extra mass there that we can't see. But again, even if they have a pretty sizable cluster of stars, unless it's very close by, it's probably going to also be very hard to do an observation like that around the black hole. The only other possibility that myself and some of my collaborators have looked at is looking at the effect that the black hole can have on light. So the gravity of the black hole can bend light around it. And so you might be able to detect it through its presence from gravitational lensing is what it's called, right? So you have light that passes nearby a massive black hole, that light gets bent in a weird direction, and then you can infer that between you and whatever background source is emitting the light, that there must be some extra object that you can't see. And this is also incredibly hard to do. But if you have the right, very special background source, it might be possible to detect small perturbations of the light due to some wandering black hole between yourself and the source. Yeah, we found in our work that that's still really, really hard and very rare. So you need to have a lot of chances to see it, to even detect it one time, just because your chances of like alignment of, you randomly have a black hole passing between you and one of these objects that's easy to detect it with is very uncommon. So yeah, the short answer is it's going to be really hard probably to detect the presence of these black holes. Something that we're still looking into about the possibilities of what sort of observational consequences could there be to something like this happening.
So say you're some future civilization in the Milky Way, or humans, if we're still around, during this merger of Andromeda and the Milky Way. Mm-hmm. This has to be apocalyptic, the beginning of this dance between supermassive black holes. Would this basically end all life in the galaxy? I mean, could anybody survive this merger, or would it be more muted if you were in, the sort of suburbs of the galaxy like we are? Is this something that ends life in a galaxy?
Oh, I don't think so at all. So the important thing to consider is, even though the process of merging galaxies is very violent in lots of ways, it's going to tear apart the galaxy and change its morphology in lots of crazy ways, the chances of two stars coming nearby each other are incredibly rare. So even though there's lots of crazy stuff happening, the solar system itself will be basically unaffected. There's not going to be some star that's going to come and destroy us. There's nothing that can tear away the solar system from itself. So it'll stay intact. The main question would be, is there some sort of radiation source that's going to blow away the Earth, right? Like some nearby supernova going off, or a nearby black hole that's growing very rapidly and emitting a bunch of X-rays. That sort of thing is more, that's the thing that can end life on an individual planet. But even a very rapidly growing black hole at the center of a galaxy, something like a quasar that's some of the brightest, most rare black holes in the universe, even something like that has a tremendous luminosity, probably isn't powerful enough to end life on a planet. It's powerful enough to do lots of things to the galaxy, but so is a supernova explosion can affect its surroundings a lot. But a supernova explosion happening in the Milky Way won't end life on Earth either. It takes a lot to do that. But again, there's lots of uncertainties. If the merger were to drive a lot of star formation and a lot of new stars get born that go supernova really quickly, and it increases the odds of being very nearby one of those supernova, then that's a possibility. But again, I wouldn't say it would end all life in the galaxy as a whole. I think that you'd be surprised at the thing that would change the most would be your view of the night sky over the next billion years or so. But to someone who's born and dies on the Earth during this merger, they won't notice any change at all, really. A human lifetime is so insignificant compared to the dynamical processes. But even if they could live a billion years, they basically just see the relative position in the night sky of the Earth change. So the Milky Way, the night sky, would no longer look like the Milky Way we see today. But other than that, I don't think that there'd be a big change there. I think the main prediction actually is that the Earth and the sun would likely be kicked further away from the center of the galaxy. But again, life doesn't really care about that too much.
It's going to be interesting times if somebody's around as this merger is about to occur. I guess some people say it actually in some ways is already occurring, outlying stars or whatever I've heard. But imagine what that would look like, because you can see Andromeda with your naked eye just barely in the night sky. And imagine what it's going to look like in the future when it's really close. I think it'll be crazy night sky. We have to go to break. We'll be back in a minute. Everybody be sure to like, subscribe, and hit the bell.
John, you're being rather secretive lately. Why?
Well, I can't tell you. You'll just leak it on the interwebs like the last time.
I only leaked because you cheaped out on my memory. What is it?
I'll tell you at the end of the show. And we're back with Dr. Michael Tremmel. Doctor, one thing about studying black holes is that it's difficult. We mentioned that in the previous segment. And part of the reason of this is because you got to look through a whole lot of stuff. When you're on the plane of the galaxy, as we are, and you're observing towards the center of the galaxy, there's a lot of gas, dust, and stars in the way. So how do you filter that? I mean, how do you say, well, this observation is not being affected by this? Do you just look at certain wavelengths of light, or what do you do?
That's a really good question. Yes, I think that the easiest answer is you look at different wavelengths. So this is how Sagittarius A star was discovered in the first place. If you look toward the center of the Milky Way in like optical wavelengths that we can see with our own eyes, all you're seeing is a bunch of dust, all the dust and gas between us and the center of the galaxy. It's nothing much interesting there. But if you change your perspective and look in, say, the radio, things look a lot different. So even in the 30s, people saw that the center of the Milky Way was very bright in radio emission. And then 40 or so years later, they found not only was it bright, but it was also very compact. And that was sort of the beginnings of actually discovering a supermassive black hole in the center of the Milky Way. And so the light, interacts with things differently at different wavelengths. So the longer wavelengths, like the radio emission, the less energetic light, is able to pass through things more freely than say optical light, which is going to interact really heavily with dust and get scattered around. Right. So when you can't see something because of stuff in the way, that's because that stuff is basically causing light to bounce off of it, and rather than come straight to us, go in different directions. But how that light interacts really depends on the wavelength of light. And so radio is really good at breaking through some of the stuff that makes it particularly hard to see the center in the optical. Also, things like X-rays and stuff like that is also really useful to use for similar reasons. So that's how we see lots of black holes in other galaxies, is by looking at X-rays, because X-rays, again, similar to the situation with radio versus optical on our Milky Way, X-rays can also penetrate through a lot of the gas that would be in the way. And so it's easier often to detect, say, a growing black hole in another galaxy by looking in the X-rays rather than other wavelengths. So yeah, that's more or less it. Is just changing your wavelength perspective so you can see the emission from gas nearby the black hole. That's another thing to keep in mind, is that we're not seeing emission directly from the black hole. We're not, detecting Hawking radiation or anything like that. It's all just the radiation coming from gas that's being directly influenced by the gravity of the black hole. Now, in the case of the Milky Way, what we can do is we can actually see individual stars near the center. So again, making sure you change your perspective on wavelength so you can actually see through a lot of the dust. We have this unique perspective where we can follow the orbits of individual stars very, very close to the black hole. So this is probably the best, most direct detection of a supermassive black hole that we have, is looking at the motions of stars very close to Sagittarius A star, and concluding that there must be some invisible, very compact mass at the center of the galaxy. Now, this is a special view because oftentimes this is special in lots of ways, in part because we're so close to Sagittarius A star, we can see individual stars, right? We can't often see individual stars in galaxies far away from us, but also because they're so close to such a massive object, their orbits are incredibly fast. So normally, we can view the galaxy as being sort of stagnant. We don't imagine night to night to see stars changing in lots of different ways, right? The Milky Way on the night sky doesn't change very much from night to night, but these stars in the center, they're moving so fast that over the course of about a decade, they've gone through an entire orbit, some of them, around this black hole. So that's incredible data that you can use to see, quote unquote, see this massive object in the center. So in some ways, it's difficult because we have lots of stuff to look through because we're inside the Milky Way. On the other hand, we do have the ability to actually to make some unique observations, right? Because we're so close, we can see things in slightly different ways. So it's sort of half and half, right? We have to look through lots of dust and gas. On the other hand, we're so close that we can sort of resolve things a bit better.
Now, these stars that are really close, orbiting within a decade, which, I mean, it's amazing to think about that because, things do change on geologic timescales, but they rarely change, at least looking at the galaxy, they rarely change on very short timescales. Now, what happens to the star as it gets closer to the black hole? Does it just get all of its gas robbed away, and does the star eventually blink out? What happens to it as it spirals inward?
Oh, that's a great question, and actually relates back to what we talked about previously. So in the Milky Way, at least, all the stars that we've seen, for the most part, survive this orbit. They're far enough away still where they're not being torn apart by the black hole. So the process of tearing apart, right, that's going to happen when, so similar to the Earth and the Moon, say, right? Tides on the Earth are caused by the gravitational influence of the Moon sort of stretching the Earth out, right? One side of the Earth is closer to the Moon and one side is further away. They feel different gravity. And so the Earth sort of stretches out slightly. And that is what causes tides on the Earth. And you can have very extreme cases of such tidal interactions where that difference in gravity from one side to the other is so strong that it can actually overcome the sort of binding force that keeps the object together in the first place. So this is actually why Saturn has rings around it, right? Is that the tidal forces are so strong that any object that's big enough that comes that close will be torn apart. And so you have this ring structure around it that would never form a moon because the tidal forces are too strong. The same thing can happen around a black hole, right? The gravity is so strong. As that gravity gets stronger, the difference in gravity also becomes stronger. And so if you get very close, the star can be torn apart. And it's a very even more violent process than other things because the star will, throughout this process, will emit a ton of light as it's being torn apart and fed onto the black hole. And this is called a tidal disruption event. And so people have been really interested in this as another way of detecting supermassive black holes, because they have, in some ways, very unique signatures. They're very time dependent, so they change a lot over time. You'll see kind of like a supernova, right? You see a supernova go off and it changes on year timescales and even week timescales. And you would see something like that here. You would see a very strong flash of light that has a very unique evolution over time as that star gets eaten. And while this isn't happening in the Milky Way, it can happen in other galaxies. And there have been some observations, say, potentially detecting some of these tidal disruption events. And it's also one potential way, like we talked about in the last part, detecting some of these wandering black holes, right? If you have a black hole with stars around it, maybe some of those stars do get close enough just by chance. And so maybe you could detect one of these black holes if it happens to be destroying a star through one of these tidal disruption processes. Now, it might be rare to happen, but if you have enough of these black holes, it's bound to happen sometime. You can place constraints on how many you expect to exist. If you don't observe anything, if you do observe one or two. So that's one way possibly we can get a handle on whether or not there's black holes way far away from the center of galaxies. But yeah, that's not happening in the Milky Way. I'd say the only really important interaction there is just gravity. The stars are moving so fast, they're moving relativistically. So you actually have to do general relativistic calculations to predict their orbits, and it changes exactly how the orbits evolve over time. But I think that's the most important thing the black hole is doing right now, at least to the stars.
That's exciting in and of itself, though, the idea of a star moving at relativistic speeds. Just the idea of it is cool. Now, let me ask you this. All right, so we have a star and we have these events that we see in other galaxies of tidal forces. Does this change depending on what kind of an object we're looking at? If we see a star, we can expect it to look like this. What of a neutron star falling into a black hole?
Yeah, I'm not a huge expert on tidal disruption events in particular, but yes, you presumably the light being emitted would look different because the star itself, what it's made out of, how dense it is different. Yeah. I mean, to sort of the initial approximation, right, is that the size of the object is going to matter in terms of what this interaction looks like. And so you have a smaller, denser object. It will have to evolve a bit differently than a larger star, right? Because we're talking about sort of this differential force of gravity across an object. So it's going to be harder to disrupt a neutron star than a normal star. And presumably it would look different. Although I think in general, it would still have the same characteristics that would sort of allow you to pick it out as a tidal disruption event rather than a bunch of other things. It's still going to look different from, say, a supernova explosion, something like that. That's why it's difficult, right? You see something and then you have to prove that it's not this and not that, and specifically this other thing. There are lots of variables to take into account. The best you can do is sort of come up with your best idea of, it was this type of star that interacted with this mass of a black hole, and we can fit the evolution pretty closely, and then you come to your conclusion that it's most likely a tidal disruption event happening.
Now tell us about your work, the Romulus simulations.
Oh, yeah. So our goal with these simulations is to, well, among other things, is to study supermassive black hole evolution in the context of galaxy evolution. Right? So we've talked so far about very detailed, small-scale physics of black holes, right? Black hole binaries forming, tidal disruption events, looking at gas very nearby a black hole. As we talked about at the start, right, to get a black hole merger in the first place, you have to start with galaxies interacting, right? And to properly simulate galaxies interacting and predict how often, how long it takes, say, those black holes to form a binary, that was one of the main goals of this simulation, is to run a simulation of a bunch of galaxies in a large volume of the universe in a way that, with enough resolution, enough detail to actually predict what the motions of black holes would look like during these merger events. And it's important to run such a big simulation because you can imagine throughout the history of the universe, galaxies change a lot over time. What mergers between galaxies look like changes over time. You don't just have two galaxies in isolation coming together and merging. You have galaxies that are changing themselves internally in a different environment that's changing over time. The environment in very early universe looks very different than the environment today. So to take all of that in self-consistently and then predict where and when black hole binaries should form and how long it takes those binaries to form after their galaxies have merged. That was one of the main goals. That was some of my earlier work with the simulation, was looking at these things, making predictions for them. And the more interesting thing that we found was that, for one, it's often actually pretty difficult to get black holes to form binaries. Only in relatively rare cases does it happen relatively quickly. Oftentimes it takes quite a long time for two black holes to come together to form a binary. And often what you have, rather than like the Andromeda and Milky Way being almost the same mass, what you often have is galaxies. One galaxy is big, like the Milky Way, let's say, and another galaxy is quite a bit smaller. And so that smaller galaxy interacts with this bigger galaxy, and instead of like disrupting the entire galaxy, the bigger galaxy doesn't really care too much. It just stays where it is. The smaller galaxy gets destroyed, gets torn apart by the gravity of the bigger galaxy, and in that process ends up leaving behind its black hole if it had one. So if you have a smaller galaxy that has a smaller black hole inside of it, that black hole, rather than make its way to the center of the bigger galaxy, will just be left on a very wide orbit within the galaxy itself. So the prediction we made is that these massive galaxies, like our own galaxy, that have gone through a richer history of these what we call minor mergers, these instances where a small galaxy interacts with the bigger galaxy. The majority of the interactions that the Milky Way has gone through, these tiny, smaller interactions, that lots of those can actually leave behind this population of wandering black holes, we call them. Black holes that exist in the galaxy long term will not make their way to the center for a very, very long time, longer than the age of the universe. And so today should be somewhere outside the galaxy, outside the disk of the galaxy, sort of orbiting around. This is purely a prediction of the simulation. There's lots of sort of caveats and uncertainties, but it comes back to the idea of how merging galaxies bring their black holes together. The most important process in that, or one of the most important processes, is that the galaxies come together themselves, that the dense structure of stars in the center of those galaxies will eventually find each other and bring their black holes along with them. But if you have a very unequal mass merger, oftentimes that dense ball of stars in the center isn't dense enough and will become disrupted, will become torn apart. And the black hole left on its own will not make its way to the center very quickly. It will take tens of billions of years, which is longer than the age of the universe, to actually get to the center naturally.
Now that seems dangerous. If you have a bunch of wandering black holes in a galactic merger, and one of them passes near to the solar system, I mean, say we're still here by some miracle, how close would it need to be to actually disrupt the solar system? Or would it just pass, a few light years away and we wouldn't even notice? Or would that be dependent on the mass of the black hole?
It definitely depends on the mass, but for a typical, millions of solar mass black hole that we would find wandering around, maybe even less massive than that, you need to still get pretty close. I would say within a few light years, maybe at most tens of light years, which is actually quite rare. I started trying to do this estimate. Again, there's lots of uncertainty in it, but all these black holes, one thing they have in common in our simulation is that they don't exist within the Milky Way disk. They're always above or below and on more sort of inclined orbits. And so it's relatively rare for them to pass through. They're only passing through the disk maybe twice along their orbit, if the orbits are close enough to do that. And so the chances that, the one time it passes through the disk throughout an orbit, it's going to also come close to a specific star is very rare. And so, I think that the chances are, 1 in billions or even more than that this would have ever happened in the history of the Earth, and it will ever happen in the next 10 billion years. And so it's very uncommon that we'd get close enough to experience this. Even more uncommon than it is for the Milky Way to interact with another star nearby. Right? We essentially don't care gravitationally about nearby stars that much. The chances of one coming by close enough to disrupt the solar system is incredibly rare, despite the fact that there's a bunch of stars in the Milky Way. So even though the black hole is more massive and can do more damage potentially, there's a lot fewer of them than there are stars, and so it becomes even less likely than that. So not very dangerous, I would say, on average. for life in general and for us in particular.
It always pays to remember that, yes, there's hundreds of billions of stars in the Milky Way, but there's also a whole lot of space.
Exactly. There's much more space between things than there are. It's actually weird. It's more likely that two galaxies will interact with each other, right, than two stars within those galaxies. So relative to the size, two stars are more far apart than the typical galaxies are relative to their sizes.
And it's interesting because that extends all the way down to the atom. The atom is mostly air, or space, just nothing. And so is the galaxy.
Very good point.
So say that the highly unlikely did happen and we did have a black hole passing a few light years away. Could we even detect it if it were just a naked black hole passing by? I mean, at that distance, can we detect Hawking radiation or would we not even know it was there unless it was interacting with the Oort cloud or something gravitationally?
That's a good question. I don't know off the top of my head what you'd expect the luminosity of Hawking radiation to be for a million solar mass black hole. My guess would be you would detect it once again gravitationally. So you would see either as it gets closer to the disk, to the plane of the galaxy, it now all of a sudden has a supply of gas, and so it will eventually sort of turn on, become bright, because it'll start eating that gas around it. That's one possibility. Another possibility is that, you detect it mostly through the fact that you're seeing a gravitational interaction between it and nearby stars, including maybe the outskirts of the Milky Way itself. But my guess is that Hawking radiation is still probably too dim. But I allow myself. I'm not sure about that. I'm more sure that it's potentially likely that you can detect gravitationally, or if it's eating gas nearby. Although I guess that's the least of our worries at that point. If it's going to come that close already, that we can see that, might already be too late. But yeah.
All right, Doctor. Thank you for joining us today.
Thank you for having me.
John, why do we have an ambiguous delivery company dropping off a case of recycled paper?
I'm analog. I'm working on my new book.
Oh, that's lovely, John. Do you think this one will sell?
What? Of course it'll sell, just as soon as I upload it.
I'm predicting there'll be a logistical issue.
We'll cross that bridge when we come to it. Wait! My book! The possum's got my book!